Sprint performance is primarily determined by neuromuscular capabilities, i.e. force and power, and technique, i.e. the ability to apply ground reaction force effectively. Therefore, developing muscular strength is considered important to enhance sprint performance. Muscular strength can be developed by using various modalities such as reactive strength, maximal strength, combined strength, and special strength. To determine the effect of these different strength training modalities on sprint performance in female team sport athletes, William and colleagues conducted a systematic review and meta-analysis, which included 15 studies. 12 studies involved female soccer players, while the other studies involved handball and volleyball players, which represented a total sample size of 362 female athletes, aged between 16 and 24 years. In total, there were 17 intervention groups and 15 control groups. Strength training programs ranged from 4 to 12 weeks, with a frequency of 1 to 3 sessions per week. Sprint distances ranged from 4.6 to 40 metres, and for analysis purposes were categorised into the following subgroups: 0 to 10 metres, 0 to 20 metres, and 0 to 40 metres. The results of the analysis confirm strength training does improve sprint performance. Specifically, there were small improvements found over 10 metres and moderate improvements for both 20 metres and 40 metres. However, the magnitude of improvement was influenced by the type of strength training. This presentation, brought to you by Talking Sport Science, will provide a summary of the different strength training modalities and their impact on sprint performance. Firstly, reactive strength is the ability to produce force in a fast stretch shortening cycle action, which is developed using plyometrics. Reactive strength can be assessed by performing a drop jump or rebound jump on a contact mat or force plate, with the cue to minimize contact time and maximize jump height. By dividing the jump height by the contact time, the metric known as the Reactive Strength Index, RSI, can be determined. Reactive strength training was found to enhance sprint performance, with a moderate to large improvement for 0 to 10 metres and 0 to 40 metres, and a small to large improvement over 20 metres. However, only 3 out of the 15 studies included in the analysis reported RSI values. The reactive strength interventions of these 3 studies resulted in an increase of 8 to 21.5% in RSI, while concurrently improving sprint performance by 3.2 to 5.2%. It should be noted, however, that the individual components of RSI, i.e. jump height and contact time, were not presented, making it difficult to determine which components were the primary driver for changes in RSI and improvement in sprint performance. Nevertheless, based on the reviewed studies, to develop reactive strength, a combination of unilateral and bilateral plyometric jumps in both vertical and horizontal directions, utilizing fast and slow stretch shortening cycle actions, are recommended. In terms of plyometric exercises, drop jumps, counter movement jumps, broad jumps, bounding, pogo hops, and hurdle hops can be prescribed to target the underlying neuromuscular mechanisms of sprinting and to facilitate the transfer of training effect. Regarding training volume and frequency, this can vary with 90 to 260 foot contacts over 1 to 2 sessions per week. Furthermore, measuring an athlete's RSI and its individual components is recommended to offer an insight into the components driving the observed changes in RSI, which can help to inform training prescription. Moving on to maximal strength, which is the ability to exert maximal force on an external object or resistance. Lower limb maximal strength is generally assessed through dynamic, i.e. back squat 1 repetition maximum, or isometric tests, i.e. the isometric mid-thigh pull. The analysis revealed maximal strength had a trivial to small improvement on initial acceleration, i.e. 0 to 10 metres. However, there was only a trivial improvement on late stage acceleration, i.e. 0 to 20 metres. The lack of any substantial improvement may be due to several reasons. Firstly, it has been suggested that improvements in sprinting performance do not necessarily occur immediately after a period of strength training. Therefore, it's possible that athletes require time to adapt and transfer the gains in strength to the movement of sprinting. Furthermore, inadequate sprinting technique could potentially conceal the true effect of maximal strength training on sprint performance. It's also plausible that the results of the included studies may have been influenced by the menstrual cycle. However, out of the 15 studies analysed, only 2 investigated maximal strength. Therefore, it's not possible to draw clear conclusions about the true effect of maximal strength training on sprint performance for female team sport athletes. As a result, a combined strength approach, which involves performing both maximal strength training and reactive or explosive strength training, is recommended, as this was found to have a large improvement on sprint performance for both acceleration and longer sprint distances. To improve both sides of the force-velocity curve, a combination of maximal strength exercises, for example back squat, leg press, lunges, at 85% of 1RM or above, and reactive or explosive strength exercises over 1 to 2 sessions per week are recommended to optimize sprint performance. And last but not least, special strength, which applies the principle of specificity to strength training by using exercises that have similar motor patterns and neuromuscular characteristics to the competition movement, in this case sprinting. For sprinting, special strength can be developed through resisted sprint training by implementing sled sprints, uphill sprints, and motorized devices to overload the neuromuscular system while replicating the motor pattern of sprinting. The analysis revealed that resisted sprint training may be no more effective than free sprint training for improving sprint performance. However, it has been proposed that sprint adaptations may be velocity specific. For example, heavy sled loads may improve initial acceleration where velocity is relatively low and force output is high, and light sled loads may improve the maximum velocity phase. Furthermore, very heavy loads, i.e. 80% of body mass, have demonstrated a substantial increase in maximal horizontal force production in male athletes when compared with free sprint training. However, the studies included in this meta-analysis only used moderate loads, i.e. 12.4 and 12.6% of body mass. Therefore, given the female athletes typically have lower levels of maximal strength compared with male athletes, heavy resisted sprint training loads, i.e. above 20% of body mass, may be beneficial for developing the force necessary to optimize acceleration in female team sport athletes. However, if heavy resisted sprint training loads are prescribed, they should be implemented with caution so it does not adversely affect sprint mechanics. Although based on the existing research on female team sport athletes, the performance benefits of resisted sprint training over free sprint training remain to be conclusively demonstrated. Therefore, compared with special or maximal strength training programs, reactive strength and combined strength training methods appear to have the greatest benefit to sprint performance. However, the evaluation of moderating variables highlighted that the effect of strength training on sprint performance can be influenced by age, program duration, and total number of sessions. Regarding age, sprint performance for both adult and youth athletes was enhanced following strength training. However, youth athletes demonstrated a significantly larger improvement in performance for longer sprint distances, i.e. over 40 metres, when compared with adults, but not over 10 or 20 metres, although they did demonstrate a slightly larger improvement in performance over both distances compared to adults. The greater response to training in youth athletes is likely down to maturation of the athletes and their lower training age. Regarding program duration, programs longer than 8 weeks resulted in a larger improvement in distances over 10 and 20 metres. However, for distances representative of maximum velocity, i.e. over 40 metres, similar improvements were observed irrespective of program duration. Furthermore, interventions with a higher number of total sessions, i.e. above 12 sessions, demonstrated a larger improvement for longer sprint distances, i.e. over 20 metres and 40 metres. However, during the acceleration phase, i.e. over 0 to 10 metres, there was no difference in performance regardless of the total number of sessions completed. Therefore, the use of a longer program duration and a higher number of total training sessions is recommended to improve overall sprint performance. It should be noted that because sprinting is a multidimensional skill, a competitive female athlete's training program will be multifaceted in nature, utilizing a combination of training methods, For example, technical training, free sprint training, and different strength training modalities to enhance performance. And that concludes this presentation. I recommend you check out the full article. The link is in the description. Thanks for listening, folks. See you next time.